Hello friends, this video on Chemical Kinetics Part 5 is brought to you by examfear.com. No more fear from exam. See, we have seen till now how to see the rate of reaction, how to find the expression for the rate of reaction. Right? So we know how to find the rate of reaction. Now the question is, this rate of reaction depends on what factors? How can I increase the rate of reaction or how can I decrease the rate of reaction? We have seen that in one of the numerical that the rate of reaction decrease over a period of time. And initially we saw the rate of reaction was more, and then gradually we saw the rate of reaction decrease in one of the numericals. That means the rate of reaction is dependent on the concentration, correct? Because the concentration was going down for reactant, the rate of reaction also decreased. Now in this slide, let's try to understand all the factors that changes the rate of reaction, because the whole kinetics is all about the rate of reaction. Let's understand the factors that impacts the rate of reaction. The first factor is the nature of the reactants. The next is the state of reactants. Third is temperature. Fourth is catalyst. Fifth is concentration or the reactants. And there's a law given to explain that. This is called rate law. We'll understand this. So we'll understand all these factors in detail now. Right? The first is the nature of reactant. See, just understand, as I told, the reaction happens when two cars hit. Now the scenario is we have this moving pillar, you can say, or tower. So I'll say the reaction will happen if the star is broken by the vehicles on the left. Correct? Now, do you think this truck here has more capacity to break the star, or this Jeep has more capacity, or this car? Obviously, the truck has more capacity to break the star, right? Because it has more powers, bigger in size. The Jeep is the next, and the sedan car is the lowest impact, right? So with this, if you compare the whole reaction with the car collision theory, the car is bumping something, maybe in this case a tower, because in the real life, when you talk about the reaction at the molecular level, there will be molecules and they'll be bumping around each other. The molecules will be discussing that in the kinetic theory, the collision theory actually for the reaction. But just understand here, in this scenario, there's a tower and this target is moving and it has to be broken down, right? So this yellow car may take 10 hits to break this target. This Jeep may take 5 hits. This big truck can break the target in 1 hit itself. So the nature of the reactant, these are my reactants. In fact, the tower also is a part of reactant here now. This whole thing is a reactant. So if you see here, the reactant plays a role, right? Reactant plays a role in the reaction. For example, if you talk about a slow reaction, very slow reaction, for example, carbon diamond to graphite, it's a very slow reaction. And a fast reaction, hydrogen plus oxygen gives water. It's very fast reaction. So if you see, the reactant type is determining the rate of the reaction. Right? It is the eagerness of the reactants or how vigorous the reactants are to form product. That determines the rate of the reaction. Correct? So the first thing to determine the rate of reaction is the reactant, because reaction is nothing but the collision between the car and this target. Correct? So for example, if you see for a fast reaction, if you take NaOH and if you see HCl, this is the base, this is acid. This acid-base reaction will give NaCl and water. So very, very fast reaction. You talk about copper and oxygen, you heat this, you get a very slow reaction. But if you copper, if you take Mg, magnesium, you little bit heat this, you get 2 MgO. It's a very fast reaction. Right? If you talk about the rusting of iron, it's again a slow reaction. This is fast, this is again slow. So if you see in all this case, the nature of reactant are determining whether the reaction has to be fast or slow. The next factor that impacts the reaction is the state of the reaction. State means whether it is in gas state, solid state, liquid state. So if you see, let's suppose in the same scenario, I have just kept the target stationary just to explain the concepts, but generally the target is moving. Now, my reactants are same in both scenarios. right? The reactants are nothing but the tower and the car. The car type is also same. And again, the goal is if the car hits this tower, that means the reaction happened. If the car breaks this tower, that means the reaction happened. If you see the gaseous state, these cars are easy to move around and they can bump this tower and break easily. But I talk about the solid state, there are so many rocks there, correct? Because these are molecules, nothing but, if you see, these are nothing but molecules. This tower is also nothing but molecule, and these two molecules will hit to form a product, right? If you talk about the solid state, these molecules are tied up with a lot of force. Right? The force inside them is very, very strong. They're tied up very strongly. These cars will not be able to move around so easily because of the rocks here. And thus, if you see similar four cars, this reaction will be fast and this will be slow. Why? Because here the cars are not allowed to move around so easily because of the presence of rocks. And that is nothing but the intermolecular force in the solid. Right? So you can see that the reaction in the gaseous states are faster as compared to reaction in liquid or solid state. So gas is faster than liquid than solid. Right? As I told, the chemical reaction takes place when the molecules heat each other. When they heat each other, they come in contact and they form product. So in the gaseous state or in the liquid state, the collision frequency is large. Right? They can hit more. This car can hit star more. The collision frequency is large, so the reaction rate is large. Correct? If you want to see the examples in real life, example sodium and iodine. If sodium is in solid, sodium will be solid always. If iodine, I am putting a gas, I get 2NaI, and this will be a very fast reaction. But the same reaction, sodium will be solid, instead of iodine gas, take iodine solid, I'll still get the same product, but this will be a slow reaction. So if you see, the state matters. This was gas, this is solid, this is fast, this is slow. Right? The reactants are same, only the medium is changing. Another example is if you take zinc powder, right, and you react with HCl, you get zinc chloride, and obviously hydrogen gas will come out. And this will be very fast reaction. If you take zinc powder, instead of zinc powder, if you take a big zinc lump, have the same concentration of HCl, you will get the same zinc chloride and hydrogen gas, but this will be slow reaction. You see, the state of the reactant is changing. In this case, it was powder. In this case, it was lump. This was a fast reaction. This was a slow reaction. But if you see, the reactants are same, the product is same, everything is same, but the reaction rate has changed because of the state of the reactant. So, state of the reactants has a role in the reaction rate. The next factor we'll understand is the temperature. If you see, the temperature, the moment you increase the temperature of a particular solution or reactant, the kinetic energy of the molecules increase. That means the speed of the car will increase here, because here the molecules are nothing but the car. And let's assume this is my target. Again, they are two different molecules, they are two different reactants actually. This is my reactant A and this tar is my reactant B. They two both react and form some product. The reaction will happen when this A can break this tar B. Now if you see on the left hand side we have low temperature scenario, right hand side we have high temperature scenario. So if you see on the low left hand side, the car is moving at a slow rate, so it is hitting the tower less. Right? Maybe if you see, but on the right hand side, this car is moving at a high speed, and thus if you see the number of collision, the frequency of collision which this car on the right hand side is making is much more than the car on the left hand side. Both are same car. That means both are same molecules. The reactant is same. The car is the same. The target is the same. That means A and B is equal to C plus D. If that is the reaction, A and B is same in both cases, but the temperature is different. Left hand side, the temperature is low. Thus, the rate at which or the speed of the molecules is low. If you see, the frequency is very low. Also, since the speed will be low, the impact to break the star will be low. Correct? On the right hand side, we have high temperature. High temperature, these molecules are going in the high temperature. The car is bumping the star at a high temperature. That means the frequency is more, plus the impact which this car on the right is creating to break this tower is more. Correct? So the temperature has a very huge impact on the rate of reaction. We'll talk about this. Arrhenius gave a very wonderful equation to understand this rate of reaction that is dependent on temperature. We'll explain this in more detail. Let's understand this from a very layman perspective. When we compare this reaction with the car, if it is low temperature, that means the car has lower speed, the frequency of collision is less, the impact is less. If it is high temperature, the car has a higher speed, the frequency of collision is more, the impact is more, so the rate of reaction is more on the when the temperature is high for a given reactant. Right? In the real life, if you see, during fever we lose more weight. Why? Because the temperature is more, the reaction is more. If you see the cooking of food also, if you try in high speed, you cook food easily. Right? The low speed, it takes time to cook food. Right? Also, as I told, the temperature is nothing but a measure of kinetic energy of the system. The moment you increase the temperature, as you have seen in the last slide, you increase the kinetic energy of the molecules, in this case cars, and that means you have more collision and more meaningful collision. And for most of the chemical reaction, we will see that for every 10 degrees Celsius rise, the rate of reaction doubles. This is an experimental thing. We'll see this when we talk about Arrhenius equation. The next role is the catalyst. See, catalyst lowers the activation energy of the system, of the whole chemical reaction. We'll talk about activation energy in the next few slides. See, they are not being consumed. They are not consumed by the system. They are not consumed. They just work by increasing the frequency of collision between the reactants. So in this case, there are two reactants, this tower and this car, let's suppose. Right hand side also we have the same scenario. This is without catalyst, left side, right side with catalyst. So they somehow increase the frequency collision. So in this case, what it has done is this tower is moving tower. The target is a moving target, but catalyst has somehow stopped this target. Since the target is stopped, the collision frequency is more. You see, both sides, the temperature is same. Since the temperature is same, the speed of the car is same. But left hand side is without catalyst, the target is moving, the number of collision per second is less. But right side, if you see, somehow the catalyst has made this target stationary. So with this, if you see, the number of collision is more, plus the meaningful collision is more, correct? Also sometimes these kind of catalysts add this kind of structure to the molecules, right? With this, if you see, they get extra power to break the target. The temperature is same, the kinetic energy is same. If you see, the kinetic energy of the car is same, but still they have got a different structure. They just change the structures of the molecules. Either they hold the structure, they hold the molecules, they make it stationary, or they change the structure. In this case, they have changed the structure of the car, and with this, the collision is more effective in this scenario on the right hand side. Right? They sometimes reduce the molecular bonding also. We'll discuss about the role of catalyst in the next few slides. In fact, the last few slides we'll discuss in details. When we understand the activation energy, we'll understand the role of catalyst all the more, right? And a good example of catalyst is the digestion of body, digestion in the body. You see, in the body, the food is digested using catalyst. Without catalyst, it is very difficult to digest food. Also, if we talk about the hydrogenation we use in organic chemistry, we use platinum catalyst. And platinum catalyst, if you see, it is not being consumed, but it provides a surface where the hydrogenation can take place, right? So this catalyst helps to increase the rate of reaction, but they don't take participation in the whole reaction. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.